So same again, I've now changed my gears. I'm now in 5th gear, which is overdrive, and it's now changed the formula again, but again horsepower coming, torque coming down the line, 300 foot-pounds through the gearbox, through 5th gear, through the final drive. It winds up with 1072.7 foot-pounds of torque, and now the RPM now is 1468.8. Again, do those same calculations. Torque times RPM divided by 52, you wind up with the same, near enough to 300 horsepower. So here it is in definition, is that when you go up the gears, so in other words you get into the longer ratios, you are substituting force for RPM, which is going to give you more speed. This is the formula for brake mean effective pressure. Now I've simplified it, so it is just down to using a foot-pound per cubic inch times either 150.8 for the 4-stroke or 75.4 for the 2-stroke or rotary. Below are the examples. I've just used 1 foot-pound as the generic answer, generic torque output, and then those are the two derivatives of each. Now, as you can clearly see, that the 2-stroke or the rotary, if the brake mean effective pressure was to be at 150.8, the same as the 4-stroke, it would have an output of 2 foot-pounds per cubic inch, which would be quite remarkable. However, as we've demonstrated before, the 2-stroke and the rotary does not develop its horsepower from a high brake mean effective pressure. It develops it by simply sheer throughput of air and fuel. We now get down to the nitty-gritty of horsepower, which we've established as airflow. So now we're going to deal with how much airflow equals how much horsepower. And for my calculations, I use 1 CFM of head flow is equal to 1/4 of a horsepower per cylinder. But this also has to be related to a vacuum depression that you're using on your flow bench at 28 inches of water. So when we apply this and we use a nominal figure for a head flow where we use 200 CFM, when we apply that head flow to a 4-cylinder, the engine is said to have 200 horsepower potential. The same 200 CFM flow on a 6-cylinder will be 300, and the same 200 CFM available on an 8-cylinder will be 400 horsepower. So what we have here is just some basic calculations that I went ahead and did just to make things really easy and really simple. So all this is about is demonstrating what happens when we do certain fuel modifications. So we go from our premium gasoline and then we switch to say E85 or methanol, and then I've also chucked in also diesel and nitromethane for a little bit of fun, just to give you an idea. So in black is the actual rating that I've declared going the 100% horsepower potential per pound of fuel. So for premium, 440 HP is, we'll class that if you could convert 1 pound of gasoline and you would be making 440 horsepower from that pound of gasoline, you would be running 100% thermal efficiency. So that's what that number is, and that just helps clarify and just keeps things simple. So when we go down to say E85, we have only 295 horsepower per pound, so its energy density is quite a bit less. But, and this is the thing that I haven't included, but anyone who knows E85 or methanol, they run a lot richer. And because of the amount of fuel that is being run, when we compare it to 14.7 pounds of air, which is a direct comparison to how much air would be consumed for normal premium gasoline, we can easily see why we pick up horsepower when we change fuel. Why? Is because the energy in the fuel and how much we are now putting into the engine has gone up. So we could run at we could lose thermal efficiency yet still gain a final horsepower number because the amount of energy that is in the fuel that we're chucking at it. Now, that isn't just the reason why people use E85 and methanol. There are other things, which is namely the ability to put lots of boost or lots of compression or both into these fuels, and that helps lift the thermal efficiency further, so we get a lot more power from our pounds of fuel that we are using. Now, possibly the greatest one that we can look at is diesel, because diesel and premium gasoline, surprisingly, they operate at very close air fuel ratios. But the reason why diesel can make so much more horsepower potential per 14.7 pounds of air is because diesel is heavier than premium. So it's effectively using its power density is higher. Using some basic sums from before, using the HP per pound, and using a basic sum that a nitromethane or the top fuel dragster will consume about 4 litres a second of nitromethane. When we project that out over the course of a minute, we'll wind up with the theoretical horsepower potential of just over 65,000 horsepower. We then we have worked it out, or it has been worked out to be that it is an approximation because there's no real dyno that you can put this on and get an actual figure. But just going by that same classic example of
so using the
track
above
length
equations,
weight of the vehicle,
we can
and the
see
time in which
that
it takes
an engine,
to go from one
this
end to
engine
the other,
requires 30 horsepower to maintain 60 mile an hour, because there's 30 horsepower worth of air resistance through air friction
horsepower
to try and cut through.
When we take 12,000
so this engine
and we
is
divide
going
it by
to
the
be
horsepower potential in the
converting
fuel, we wind up
X
with
amount of fuel into
18.46%
30
thermal efficiency.
horsepower.
So, in other words, a nitromethane or the top fuel dragsters are able to convert 18.46% of the chemical energy in the fuel to mechanical energy that is able to drive the car. In all of the examples that I have given, all of them have been under full throttle conditions. Now, a normal road car does not spend most of its life under full throttle conditions. It is spent under a throttled conditions, where we limit the air supply, which then limits the amount of power and torque that an engine can produce. So continuing on with our 30 horsepower engine fighting 30 horsepower air friction to maintain 60 mile an hour example. When we're in that situation, our engine speed does not change. So if we then modify a vehicle to increase torque, the application of it increases, so we now have to lean out. So we've got to back off the airflow to generate the 30 horsepower. And we do that when you look at our torque times RPM divided by 5252. Now, because our RPM hasn't changed, our torque will go up. So naturally, if we need to make less power, as we've demonstrated with power as airflow, we simply have to reduce the airflow by reducing the throttle opening percentage. We now get to the final piece that I wish to teach, and that is reading the dyno graph that you were given. Now, in this example, I'm not putting up numbers, but it's just merely looking at the curves. Now, we all know that the crossover point is 52 RPM, so in this case, that'll be where the two lines cross. So that's your RPM point. Horsepower and torque are going to be the same, so naturally they're going to cross there. The point that I'm trying to get across is that when we look at a dyno curve, we need to be, instead of looking at things as torque and horsepower, it would be more of a accurate representation to read the dyno curve as the torque line represents brake mean effective pressure, and the horsepower line represents total airflow in 60 seconds. Looking at the addition of the red and the black line, we notice a distinct trend as to how the engine now performs. So over the first 3/4 of the RPM, the brake mean effective pressure on the red line will be higher, and this is also attributed to what people call volumetric efficiency. So we have altered things like cam timing, ignition timing, fueling amounts, and then we can also alter things like exhaust and intake lengths to generate a much more improved and higher torque curve than what we had before. However, because every engine is ultimately air starved, we get to the point where the cylinder heads can no longer flow the air, and they simply become a restriction. The energy required to get the air into the cylinders no longer is greater than the energy that is being trapped. So that is when that is when brake mean effective pressure begins to fall away. So when we look at these two curves, the first thing that most people will point out is that the blue line, because it has a higher horsepower number, must be the faster vehicle. And in reality, it's not. It is only faster in the RPM band that is above the torque curve, where the torque curve of the green line goes above the red. That is the only area that this engine will out accelerate the red curve. So be mindful of chasing only horsepower for performance, because going through, if anything that I have hopefully shown you and taught to you, and now it is my case to swoon you to change your mind about everyone's performance goals when it's horsepower orientated. They shouldn't be that way. They should be focused on torque and focused on the brake mean effective pressure and generating as much of it as they can from as little amount of fuel as possible. And that way you will have a very fuel efficient engine, you will have a higher performing engine, and you will have no hesitation for throttle response or ability to climb hills and higher gears than other people. And from that, you'll be able to go to and from the track and not consume as much fuel. and it also means that when it comes time to going and doing your emissions testing, you will also be significantly under the HO emissions and hydrocarbon emissions, because you are burning the fuel more efficiently than what you were before. So that is my long-winded presentation on torque and horsepower. If you've got to the end, thank you very much. Yeah, that's about all for now. I will do another one lately. See ya.